radio astronomy. He still holds a joint appointment with Manchester. So he's published seminal papers on quite a few aspects of pulsar research. One, I'll just mention one or two. The intermittent pulsars, which he and his colleagues discovered first off, showed that there was a close connection between the pulse emission and the rate of slowdown of the pulse, which showed that the slowdown was due, at least in part, to currents flowing in the magnetosphere and not simply to magnetic dipole radiation. So that was a very important result. He's probably best known for his work on the discovery and analysis of the timing of the double pulsar and the test of general relativity, and it's that he's going to talk to us about today, the title Probing Gravitation with Pulsars.
Thanks, Steve. Good morning, everyone. So I had some very good introductions from Scott and Nanda and superb preparation for this talk. So my introduction will be very short. I'm going to talk about pulsar timing and just to demonstrate again the amazing precision that we can achieve with timing pulsars and binary pulsars in particular. And then go back in history and look at the first binary pulsar and give you an update on that was recently published. And then talk about the double pulsar that we just mentioned. Talk about relativistic spin precession and also say a little bit about alternative theories of gravity. And hopefully have some time to talk about what's going on in the future, hopefully. So this is just a more or less incomplete list of things you can do with binary pulsars in terms of gravitational physics. We have a number of relativistic effects that we can regularly observe in relativistic binaries. But we can also test deep principles and concepts embedded in the theories of gravities, like the Stock Fluence principle and so on. And I hope I'll cover those as well to some extent. So our laboratories are these binary pulsars that Scott already introduced. We know about 140 binary pulsars. That doesn't include probably unpublished sources, with the shortest period of about 95 minutes and the longest period of about 5 years. We have all sorts of companions from white dwarf to Newton stars, but also planets and main sequence stars companions. And we have, of course, one double pulsar, which I will talk about more later on. Our experiment is actually quite simple and clean. We just follow the pulsar as it falls in the gravitational potential of a companion, and as both follow in the gravitation forward in the gravitational potential of the Milky Way or globular cluster. And so what we do is we track how this pulsar falls in that gravitational potential, and we can do this with very high precision. And just to show you similar numbers, I won't expect you to read those necessarily in the back, but these are, for instance, the masses of Newton stars. We can measure with the precision, last digit is the uncertainty, the mass of white dwarf companion, the mass of recycled millisecond pulsars, the mass of main sequence star companions, and of course, or more surprisingly for some of you, we can even measure the mass of Jupiter and its moon to about a precision of 10 to the minus 10 solar masses. So that's pretty cool. This is the number that Scott already showed. I just want to point out the precision here is 2 attoseconds. That's usually a unit we don't usually use in astronomy, but in pulsars we have to get used to it. Periods, for instance, we can measure the period of the double pulsar to a few hundred nanoseconds. We can measure, this is an even smaller eccentricity that Scott mentioned, 3.5 times 10 to the minus 7. This is the smallest yet significantly measured eccentricity for binary pulsar. We can measure very high precision hysterometry. This is the same 0.37. This is a result in Swimmer group. We can measure the distance to this pulsar to plus minus 1 parsec, and we can also measure proper motions to a precision of a micro arcsecond per year. And of course, we do test of general relativity. I go into that in more detail later on. I just want to point out one result that we saw yesterday in this conference, a nice new result on the constancy of the gravitational constant of the order of 1.2 to 12 times 10 to the minus 12. And Scott mentioned the pulsar timing rays, and I'd like to sort of put that also in a kind of precision context. So the precision, the limits that these three timing rays, the EBTA nanograph and the Parkes pulsar timing ray achieve, is essentially equivalent to measure a length difference of about 100 meters over a distance of 1 light year. That's how precise we are. Not quite precise yet to make detection, but a factor of a few hopefully will suffice. And in the future we can do better things, and I come to that later hopefully. So let's go back to 1974, 1975, when the first binary pulsar was discovered. This is, of course, the Hall-Taylor pulsar, 1913 plus 16. This is the PA velocity plot, where you can immediately see this is an eccentric binary, and the Doppler variation of the spin period of the pulsar changed between 58.97 milliseconds and 59.06 milliseconds at the top. It's a 7.5 hour binary. Eccentricity is 0.6, and what you see one of the Newton stars as a pulsar with that spin period. Soon after discovery, the Hudson-Taylor noticed that the orbit cannot be described simply by a Keplerian orbit. As Scott pointed out, we use 5 Keplerian orbits usually to describe a normal orbit. In this case, the binary period, the size of the orbit, the eccentricity, the longitude of periastron, and the time when when the stars have the closest approach. If the orbit is not Keplerian anymore, but relativistic, we have to correct our description of the orbit by adding so-called post-Keplerian parameters. These are theory-independent corrections to our timing model that Scott described, And the nice thing is they're really theory independent. We can measure the value in a completely independent way and then compare those values with predictions for a specific theory of gravity. And I'll give you the example how we do this with the Hall-Taylor pulsar. So for instance, one of the easiest things to measure is the advance of periastron. This is the change of orbit in space, just like we see in Mercury. And this is the equation as you would expect it for general relativity. So we measure the left-hand side with the observed value shown underneath. And we can equate this to the expectation in general relativity on the right-hand side. We can also measure gravitational redshift. That is, clocks are going slower in deep gravitational fields. So in this case, we have an eccentric binary, and as a result, the distance between the two pulsars, or the two Newton stars, changes as a function of orbital phase. So at some point, they're closer to each other, feel a deeper gravitational field of the companion, and the clock goes slower. At some point further on, they're further apart, the gravitational field is weaker, and the clock goes faster. And that's observable with that value. So as you can see, again, you have an equation that shows the dependency and relativity on the Keplerian parameters and the two masses of the system. So we have two equations, two measurements, and we can solve that set of two equations easily to derive the masses. So if you do that, you can measure the masses of the two Newton stars very precisely under the assumption that general relativity is correct. Now the beauty about the experiment is that we can show that all these so-called post-Keplerian parameters can be written as function of these well-measured Keplerian parameters and into two masses that we just determined. So if you measure any other parameters, you can take your two masses and predict what that value should be for a given theory of gravity. For instance, for the Hall-Taylor pulsar, as you will know, another post-Keplerian parameter that was measured is the shrinkage of the orbit due to the emission of gravitational waves. And this is probably one of the most famous plots in pulsar astronomy. Here you see the change in periastron time as a function of year, and it's changing because the orbit is shrinking every day because the system loses energy, which is taken away from the orbital energy due to the emission of gravitational waves. And this is the equation as you would expect it in general relativity. And again, you have, apart from some constants, the Keplerian parameters, and here the orbital period eccentricity plus the two unknown masses of the system. So you take the two masses that we just determined, plug it into the formula, and you get a certain value. The problem with that particular case is, however, that the observed value is not identical to the GR prediction. And the reason is not that GR is wrong, but the fact that the pulsar system is actually falling in the gravitational potential of the Milky Way and has a relative motion towards the center of mass of the solar system. And that leads to these two contributions that are shown here in this equation. So the first is the relative motion to the solar system, and the second is an acceleration in the gravitational potential of the Milky Way. If you know this, how the pulsar falls in the Milky Way, we can correct for this, and this is exactly done in the right-hand plot, where this correction here has been calculated for the known parameters of the pulsar, and once you do this, the expected value that is predicted from GR is indeed consistent with the observed value. But this is also the problem why we haven't been able to improve the accuracy of the Hall-Taylor test for now almost 20 years, because it is our limited knowledge of this particular systematic effect that that prevents us from making a better correction and hence a better test of GR in this particular case. But the Hall-Taylor pulsar is not the only pulsar anymore where we see the emission of gravitational waves. It is in fact not the most accurate and not the most luminous source anymore. This is a list in terms of ranking of gravitational wave luminosity, and you see this is now commonly observed. This is very nice. And of course you also see that the first spot is now taken by another system, which we simply call the double pulsar. The double pulsar is a unique system as we have two active radio pulsars orbiting each other in an orbit of just 147 minutes. It's an old 22 millisecond pulsar orbited by a young 2.7 second pulsar. If you calculate the orbital velocities you get from the change in spin field, for instance, you immediately derive orbital velocities about 1 million kilometers per hour. And it's an amazing system because you see the edge on. As you can see now, it is actually, the young pulsar is actually eclipsing the radiation from the fast pulsar in the background. And that lasts about 30 seconds during the orbit of the system. On the left and the right-hand plot is a beautiful plot made by Mark McLaughlin. Where you can see, maybe not in the background, you can actually see the pulses of the young pulsar as a straight line when you have taken out the Doppler variation, and then maybe in the background you can see some faint parabolas, which are the signals of the fast pulsar being picked up at the same time as they both shine towards Earth. Having two compact objects within attached clocks in such a compact orbit with such high velocities makes the system an ideal laboratory to test relativity. I'll tell you more about that in the next slides. But before I do that, I just want to list the cast of collaborators, which are too many here to name a name. So the other thing, of course, it's more compact than the Hals-Taylor pulsar. This is, of course, a very nice feature. And here, the relative size of the orbit is shown in scale. In fact, the double pulsar orbit would fit easily into the Sun. But more importantly is that the double pulsar is actually much closer to Earth, just about a kiloparsec compared with the about 8 kiloparsec that the Hals-Taylor pulsar is away from Earth. So here we know the local acceleration quite well. The relative acceleration to the solar system is more or less negligible for now. But also, of course, the unique feature of the double pulsar is that it's a dual line system. So we have the ability to measure two orbits because we have two clocks orbiting the same center of mass. And so Kepler's law just simply tells you the size of the orbit is just the inverse ratio of the masses of the two systems. And we can measure that precisely, and this is shown here. Note that this value, this is a constraint we have for the first time, is a theory-independent value, at least the first post-Newtonian order. We also, of course, see this advance of periastron, which in fact is 4 times larger than that of the Hals-Taylor pulsar, and much, much larger than, for instance, the value that we see in Mercury. For instance, the double pulsar orbit rotates around in space in about 20 years. Mercury would take about 3 million years for that. And so we measure a precession rate of nearly 17 degrees. And if you remember that equation that I showed you before, how the rate of the precession depends on the masses, we now can easily calculate the sum of the two masses of the two Newton stars. We can combine that with the mass ratio. We have again two equations, and you can see that we can actually derive again the mass of the two Newton stars to very high precision. And that allows us again now to make a prediction of what other relativistic effects should be. We again measure the same gravitational redshift, and here I always quote, as you can see now, so this is in this case 383.9 microsecond, and I always quote the consistency agreement with GR next to it. So in this case, this is a 0.2% test. We also see the Shapiro delay that Scott was referring to for the most massive Newton stars. These are the Shapiro delay curves that we obtained. The one is the first one we published in 2006, the one is a more recent one, and you can see also this orbit happens to be very close to 90 degrees, so close that in fact the distance which this pulsar signal passes the companion in only 20,000 kilometer distance. And again, you see, oops, this is not right. GR value should be good to 10 to the minus 5. This is one, sorry. We also see, of course, the shrinkage of the orbit. Here we can measure, for instance, that the orbital period is shrinking every day by 107.8 nanoseconds. So that means that every day these two Newton stars will approach each other by 7.152 plus minus 0.018 millimeters. And again, that's an agreement with GR to a precision of 0.1%. That leads to a merger of these two Newton stars in 85 million years and produces this amount of gravitational wave, which is shown in this very nice animation made by the Albert Einstein Institute. So this is indeed the best test for the existence of the gravitational waves and the fact that they follow the quadrupole emission prediction of generativity, and I come back to that later on. Just to show you, this is the Hals-Taylor plot that I showed you before. This is the prediction of what you would see for the double pulsar, and these are our measurement points. So this is not a fixed direct line, this is just a prediction. As you can see, our data fits these predictions amazingly beautiful. I come to another test that we can do with a double pulsar, which is even more exciting, I think, which is the fact that we can measure how its spin should precess in space due to the curvature of space-time. This is called geodetic precession and has been measured in the solar system, for instance, very nicely with the gravity probe B or the Lego satellites. But also, if you have a pulsar, which is essentially a spin orbiting the curved space-time of the companion, you would also expect that the pulsar spin changes direction with time. And that had been predicted immediately after the discovery of the binary pulsar in 1974. But it took us to the double pulsar to actually make a quantitative measurement of that. And the amazing, beautiful thing is that it can use these eclipses. And you see the eclipses here. This is when the pulsar is on, then it gets eclipsed, and it gets on again. And you have two different eclipses separated for a couple of years. And you may think that these data points are actually random, but in fact they're not. More McLaughlin, which analyzed the data, realized that these data points were actually separated by half the period of B, the first part, and the full period of B, the second part. And I showed this little animation here, which describes this effect very beautifully. So we have the pulsar A in the background, pulsar B in the foreground, the slow one, and as you will see now, we start to block the light from the background source, and we see this exactly the features that we see in the real data. And what you can see is that the pulsar A is sometimes visible, like now, blocked, visible, blocked, visible, blocked, visible, blocked, and then we come to a phase where it's blocked for a full period of B, like now, visible, blocked, blocked, visible, blocked, blocked, visible, and so on. And so this is a pure geometrical effect, which just depends on the orientation of the spin axis. And at the end, you can see the red data that we overlay on the model. You can see that we can reproduce every single peak in our measurements. And this is beautiful work that was led by René Breton, a PhD student at the time at McGill. So every single peak can be reproduced. And by tracing this as a function of time, we can actually, here you can see the eclipse pattern as it changes with time, and note that the orientation of the spin axis slightly changes with time as well. We can actually do a global fit and derive the rate of the precession, and this is consistent with the GR's prediction to a value of 0.93 plus minus 1.3. Genetic recession, of course, was of course first discovered in the Hals-Taylor pulsar. This is the discovered observation in '98 with the atmospheric telescope, and you can see a more recent plot that we did a couple of months ago. It still follows the prediction that the Hals-Taylor pulsar will actually disappear in the year 2025, and the effect of genetic recession is actually a good verification that supernova explosions are asymmetric. And again, this is something we now routinely observe in binary pulsars, and therefore I won't go into detail, but you may want to listen to Gregory's talk in the next session. He will talk about another system where we do this. Just a few words about tests of alternative theories of gravity. One of the most best tested theories, or developed theories I should say, is tensor scalar theories, where we add a scalar field to the metric, which is then, for instance, in this case, coupled by a linear and quadratic term. This is a quite complicated plot, but the point is just want to make here, just to take along, is that for tests in the solar systems, you may not necessarily be able to pick up the effects of a scalar field, and it really needs binary pulsars to do that, because only then you come in a range that is where the strong field effects are strong enough that you can actually see measurable effects that are beyond the solar system limit. Here, what you would like to have is a binary system with completely different scalar charges. So in a Newton star, like a double pulsar system, we have actually two Newton stars with similar scalar charges, and so the effect of dipole radiation, which would then be predicted, is rather small, because the difference in the terms here is more or less zero. What you would like to have is a system with different scalar charges, like a pulsar black hole system, which would be ideal, because the black hole doesn't have any charge and that difference is maximized, or at least you should have a white dwarf system and a pulsar. And this is just a nice work that we've done in Bonn recently. This is a pulsar 1738 plus 033, which we have very nice optical observations of the white dwarf companion, where we can measure the mass ratio, and from the timing with the radial pulsar measure the mass of the companion and the pulsar very precisely. And we know therefore the masses theory independently and can predict whether, for instance, dipole radiation, which is predicted in like tensor scalar theories, is existing. And again, I don't have much time to go on these plots, but indeed the predictions are only consistent with quadrupole radiation and not with gravitational dipole radiation. By the way, it's also a nice result for the constancy of G as well. You can put this in a quite complicated plot where we plot these linear and quadratic term of the metric coupled into the scalar field. In this plot, generativity would be in the origin of this plot. Tensor scalar vector, Brown sticky theory would be on this y-axis, and everything above the line is forbidden, and everything below a line is just consistent. And this is the new line of the pulsar, and you can see this is much more constraining than the solar system test for most of the parameters. And even though for Brown sticky theory, this pulsar test is just a factor of 2 or so worse than the best solar system test that we have. We can also constrain tensor vector scalar theories. And in fact, our data show that they have to be fine-tuned to be consistent with our observations. And tensor vector scalar theories are therefore interesting because they are one realization of a relativistic Mond theory, which is still popular with some astronomers. But according to our data, we would like to rule this out. I just want to highlight one poster. Poster 251. I won't have a chance to go into details here, but it's a test where we can essentially test whether there are preferred frames existing in the universe, and this is the test which is much better than any solar system test that we have derived today. So for more details, see poster 251. I'll finish up with 2 slides on what we're going to do in the future. Of course, we would like to find even more pulsars with even more sensitive telescopes, and the best telescope is going to happen in the future is the Square Kilometer Array, which will discover nearly 30,000 pulsars in the Milky Way, among which will be 2,000 pulsars, millisecond pulsars, which would be superb for testing, for detecting and studying gravitational waves. And look for the talk in the next session at KTD for more of that. But we also find pulsars around black holes. And so if you find a pulsar with around the black hole system, even with a 100-meter telescope, you can do some very nice measurements which will supersede all existing tests, even those of Gaia to some extent. And if you have FAST or the SKA, this would be by far the most superb test for testing alternative theory of gravity that we have today. More excitingly, however, perhaps, is the discovery of pulsars around Sagittarius A star, where we then could measure the mass of this central mass black hole in our Milky Way to a precision of 1 solar mass. This is for a rather ordinary pulsar in a rather ordinary orbit. So if you find a pulsar around Sagittarius A star, you can measure the mass of Sagittarius A star to 1 solar mass. We can also measure the mass to a precision of 1.1%. That allows us to test the so-called cosmic signature conjecture to see whether every astrophysical black hole has an event horizon. And we can also test the nova theorem to about 1%. And for more details, you should have listened to the talk yesterday in Nova. And I leave up my summary conclusion. Let me just allow one last sentence. Einstein is supposed to have said that he would have, if he wouldn't have been a physicist, he would like to have been a musician or a lighthouse keeper. I think he should have been a pulsar astronomer, a cosmic lighthouse keeper. I think he would enjoy it immensely. Thank you very much.
Thank you, Michael. We are out of time, but maybe 1 or 2 questions. Up back there.
Is there any possibility, do you think there is any possibility to estimate the limitation of the dark matter nearby the binary pulsar or pulsar from the signal from there to the Earth.
So what exactly was signal? Dark matter. There have been some interesting papers which you can do expect some microlensing events with pulsars. So in principle it's possible, but I think we should have a better density of pulsars across the sky to make that a realistic chance.
Fred?
That was wonderful, Dr. Michael. Well, I'm going to ask you the same question. Where were the wonderful measurements of the double pulsars made?
I meant to say that, yes, sorry, Fred. Thank you for prompting me. The vast majority of those beautiful data points that you've seen have been made with the GBT, in particular 800 megahertz, which is the slow frequency. And there's no other telescope in the world where you can use 800 megahertz in that quality. So I think it would be a rather daft thing to do to close it down.
Okay, so I think we have to wrap it up there. So we've had 3 great talks, and I'd like you to show your appreciation to all 3 speakers.